Hello, I'm going to talk about Niven's theorem today. So, first, let's read the statement on what Niven's theorem is. So, first of all, let's read. So there's an angle theta in the range 0 to pi over 2. And what the theorem says is that the only values of theta such that theta over pi and sine theta are rational is when theta is 0, theta is pi over 6, or theta is pi over 2. Okay, so we'll first show instead, we'll show instead that if pi over theta and cosine theta are both rational, then theta is inside the set of 0, pi over 3, and pi over 2. So this implies the result because they pair up, basically, because sine theta will correspond, the sine theta being 0 corresponds to cosine theta becoming 1, which means that these two match up. Similarly, these two will match up, and these two will match up. So first we address the lemma, and the lemma is the following. So for any integer n greater than or equal to 1, there exists a polynomial fn of x such that fn of 2 cosine t, where t is a real number, equals 2 cosine of n times t. But there's also another restraint. Degree of fn must equal n, and fn must be a monic polynomial with integer coefficients. Okay, so let's try to prove the lemma first. We'll proceed by induction on n. So when n equals 1, f1 of x, if we set that as x, then it works because 2 cosine t equals 2 cosine t, so that's pretty easy. For n equals 2, if we set f2 of x equal to x squared minus 2, then f2 of 2 cosine t equals 4 cosine squared t minus 2, and which is equal to 2 times 2 cosine squared t minus 1, which we can use the identity cosine squared t plus sine squared t equals 1, and we can easily get that this is equal to 2 times cosine of 2t. Okay, now for n equals 2, we're gonna kind of generate a recursive formula, I guess. So first of all, recall the identity. 2 times cosine alpha times cosine beta equals cosine of alpha plus beta plus cosine alpha minus beta. So this is a trig identity. And now we're going to apply this identity like the following. So 2 times cosine n minus 1 times t cosine t equals cosine nt times cosine n minus 2t. Minus 2 times t. Okay. Now we can rearrange this equation to solve for cosine of nt. So, wait, I think I made a mistake here. Let me just quickly fix that. Okay. So now what we do here is we solve for cosine of nt. To be exact, we're solving for cosine of 2 times cosine of nt. So if we solve for 2 cosine nt by rearranging, we get 2 cosine nt equals this value times 2 cosine t minus 2 cosine n minus 1 n minus 2 times t. Okay, so now we could keep on rearranging, but notice that this is from the case when n is equal to the case when it's n minus 1. So the induction hypothesis for n minus 1, we know that there exists a monic polynomial with integer coefficients such that 2 cosine of n minus 1 t equals f n minus 1 times 2 cosine t. So we can equal this with this one, because there exists such a polynomial by our induction hypothesis. And the similar thing can be done here with f of n minus 2. So what we get is that if we set fn of x as x times fn minus 1x minus fn minus 2 times x, then it will satisfy our equation. Fn 2 cosine t equals 2 times cosine nt. So we now go back to the main problem. We're going to assume that theta over pi and cosine theta are both rational. And since we assume that theta over pi is rational, we can write theta over pi as 2k over n, where k and n are integers, and n is greater than or equal to 1. And we also assume that cosine theta is rational over here. Now we're going to consider c equals 2 cosine theta, and since cosine theta is in rationals, then 2 cosine theta is also in rationals. So fm of c equals fm times fn of 2 cosine theta, and if we plug in 2k pi over n for theta, then we can get this result over here. And by our lemma, so this is our lemma over here, we can write this as 2 times cosine n times 2 pi k over n, which is equal to 2 times cosine 2 pi k. Since k is an integer, this is equal to 2. Okay, so what do we get? We see that fn c minus 2 equals 0, so c is a rational root of the monic polynomial fn x minus 2. Okay, well, we have to note that all the coefficients are integers, and this c is a rational root, and also that fn x minus 2 is a monic polynomial. So by the rational root theorem, because it's monic, c must be an integer. Okay, but now we do some inequalities over here. So the absolute value of c is equal to the absolute value of 2 cosine theta, but this is less than or equal to 2, which means that c can only be negative 2, negative 1, 0, 1, or 2. And since theta is in the range 0 and pi over 2, c can only be 0, 1, or 2. And each of these corresponds to theta being equal to 0, pi over 3, or pi over 2. And this will imply the result as desired. Okay, so that concludes our proof of Niven's theorem, and I'll move on to one application of Niven's theorem. So, one application. Can the vertices of a perfect n-gon have only integer coordinates in the xy plane if n is greater than 4? So the answer is no, because suppose so we first gonna assume for the sake of contradiction that all the vertices of the n-gon are integers, namely like x1 comma y1, x2 comma y2, blah blah blah. Well, I'm gonna assume that they are arranged in clockwise order, and these are adjacent. We're gonna first define g of x and g of y, which are kind of like the center of the perfect n-gon. So the perfect n-gon the center of the perfect n-gon has the formula gx comma gy. So now we're going to translate the n-gon by minus gx comma minus gy, such that gx comma gy, the center of our n-gon, is mapped to the origin, because we want to do some rotations. Okay, after it is mapped to the origin, then we first refer to the diagram over here. And we're going to now interpret everything in the complex plane. Okay, so we're going to first consider where x1 comma y1 and x2 comma y2 are mapped. So x1 comma y1 is mapped to x1 minus gx comma y1 minus gy, and x2 comma y2 is mapped similarly. And we can see that the angle between them after they are mapped is 2 pi divided by n radians. Okay, so now we're going to assign rational numbers a, b, c, d such that a equals x1 minus gx, b equals y1 minus gy, c equals x2 minus gx, and d equals y2 minus gy, for simplicity. Okay, so basically what we're saying here is that if we interpret this in the complex plane, we're going to rotate by 2 pi over n from a plus bi to get c plus di. So we can write the equation like this, which means that cosine of 2 pi over n plus I sine of 2 pi over n equals c plus di divided by a plus bi, which I've shown here that both of these are rational, because rationals are kind of closed in multiplication and division and addition as well. Okay, so now we're gonna compare our I would have to say like parts, complex parts and the real parts. So since this part is rational, we can see that this part must also be rational. So sine of 2 pi divided by n must be rational. But we also can see the similar thing. Cosine of 2 pi of n must be rational. Okay, so we're going to assume there exists an n, a natural number n, greater than or equal to 5, such that sine 2 pi over n and cosine 2 pi over n are both in rationals. So we're going to let theta be equal to 2 pi divided by n. Well, you can see here that theta divided by pi is in rationals, and we also assume that sine theta is in rationals. So now we can use Niven's theorem right here to say that theta must either be 0, pi over 6, or pi over 2. But now, since n is an integer greater than or equal to 5, clearly theta cannot be equal to 0 or pi over 2. So this means that theta equals pi over 6. And if we solve the equation, we get n equals to 12. But if we plug that into cosine 2 pi over n, cosine 2 pi over 12 equals square root of 3 over 2, which is not a rational number. So this is a contradiction. Hence, there are no such, so our assumption is wrong over here, which means the answer is no. Thank you for listening to the lecture about Niven's theorem. I hope you guys enjoyed it.